Alright gang, here we go. This is Physics Unit 2, Part 6. We're going to talk about everyday forces. So we're going to talk about weight versus mass, kinetic and static friction, and then a couple other little random things that we got to cover. Alright, so first up, weight versus mass. Alright, so this is one of those big things that lots of people screw up. They assume, weight and mass are the same. They are not the same. Okay, mass is defined as the amount of matter that's in a subject. Okay, so when we talk about matter, we're talking about its mass. Okay, so we take grams, kilograms, so on and so forth. The kilograms are the SI unit for mass. Okay, weight though is a measure of the gravitational force on an object. All right, and so these are newtons, which is the SI unit, or even pounds, lbs. Right. This is how we weigh ourselves when we go to the doctor. We weigh ourselves in pounds. Okay. Now the problem with this is that it depends on the acceleration of gravity, and you know all this. You've all heard the term, the phrase, "You weigh less on the moon than you do on Earth," and that's because the acceleration of gravity on the moon is far less than it is on the Earth. All right. So in order to calculate your weight, you simply take your mass and multiply it times the acceleration of gravity. Okay. So your weight equals mass times the acceleration of gravity, where ag, this should be an a up here, and this should be a subscript g. Okay, mass times the acceleration of gravity. All right, where acceleration of gravity is 9.81 meters per second squared. Now, and also in order to keep things kind of simple, right, we've always been using as acceleration due to gravity is negative 9.81, so you could always think of it as negative mg. So our weight is equal to negative mg. Okay, and that cancels out the negative for the negative 9.81. All right. So it also depends on the location. Acceleration due to gravity does vary slightly with each location on Earth. Okay, but for the most part, it's pretty much 9.81. Okay, and it's obviously going to be different on different planets. All right. Next thing we need to talk about here is called the normal force. We mentioned this back before when we were talking about Newton's first law and force diagrams and so on. The force that's perpendicular to the surface of whatever object it's on is known as the normal force, or the Fn. Okay, and this is, it may equal the force of gravity, like it does here. Notice that because this is a flat surface, the force of gravity and the Newton force, or the normal force, are equal to one another. Okay, the normal force and the force of gravity are equal to one another, but it does not necessarily have to be. So here, the normal force and the force of gravity of this box on this ramp are not equal to one another. And so therefore, in order to find your normal force in this case, you have to take the mass times the gravity times the cosine of theta, and theta is this angle right there. All right. Notice that, like, interesting phenomenon is this angle here is also going to be exactly the same. All right. And we'll do a practice problem here in a minute where you have to calculate the normal force for a cockeyed thing. All right. Next couple of things, we're going to talk about friction. Friction is any force that prevents motion. All right, that's just the general definition of friction, or resist motion. Specifically, static friction is the friction that something experiences when it's standing still. You've probably all noticed that, like, if you take something heavy and you try to start pushing it, it always takes a little bit more energy to get it started, and then once it starts going, it's easy. Right, or easier, right, depending on what it is. But getting it started always takes that little bit of extra energy. Okay, so for example, pushing this orange juice, okay, you're pushing it, all right, the hand is pushing it this way, well, this way in your guys' image, this way, this is our hand pushing it force, and this is the force of friction that the orange juice is experiencing. So this is essentially a free body diagram of our orange juice. All right, so excuse me. The hand, oh my goodness, the hand is pushing to the left, okay, and the force of friction is pushing to the right. All right, and now specifically, this is the static friction. So right now, because the force pushing it and the force of the static friction are absolutely equal to one another, then we have no motion. Okay, so they're equal to each other, so we have absolutely no motion. If our static friction changed, would it change if F was reduced? So if we stopped pushing as hard, would our F of S change? Yes, it would change. Remember, Newton's third law says the the action, nope, I'm lying to you, it doesn't change. Okay, so the force of friction is always going to remain the same, even if we stop pushing it hard. However, if we push hard enough and our F is increased significantly, then our force of friction will change because it'll go away because we've gotten rid of it, and the static friction goes away because our object is no longer static. Okay, it's going to be a kinetic friction. All right, so here we've got Fk for kinetic friction. All right, this is the friction that occurs when we're already pushing our object. So we've got our orange juice, and we just barely got it started by pushing it. All right, beat the static friction, and now we just have to continue to beat the kinetic friction in order to keep going. Notice that it does not depend on the speed. No matter how fast you're going, the kinetic friction is always going to be the same. So based on this, we can figure out what's going on. We can figure out if it's going to move or not. And all we have to do is look at the force vectors, right? So the force vector pushing it to the left is greater than the force vector of the kinetic friction pushing back on it. So therefore, we're going to have an overall movement to the left. All right, so the jug will be accelerating to the left because it's got a force, and we know force equals mass times acceleration. So if we have the mass of the jug and the force to the left, we know that we'll be accelerating. Okay, so how could we have the person push the jug at a constant speed? Well, constant speed, this really means that our acceleration is equal to 0. So how do we make it so our acceleration is equal to 0? Well, all we have to do is make sure that our F net is equal to 0, right? So we need to make sure our F net is equal to 0. Okay, if our F net equals 0, then we're golden. Okay, so how do we make sure our F net is equal to 0? Well, we just have to make sure that the force we're pushing on the orange juice is exactly equal to the kinetic friction. If it's less than that, then we'll have some sort of acceleration, either speeding up or decelerating. Okay. All right. Let's see. So click on the PowerPoint that I've posted on Google Classroom and watch this. It's pretty interesting. It does a good job kind of illustrating these. We'll watch these in class. All right, a couple of important formulas that you need to know. Okay, the force of friction is equal to mu times F, the normal force. Okay, so the frictional force is directly proportional to the normal force. That makes sense. The harder you're pushing down on something, the harder it is to keep it going. The more ways, the harder it is to get it started. So the force of friction is equal to mu times Fn. Mu is called the coefficient of friction. All right, and it's determined by the nature of the two substances that are interacting with one another. U sub S is for static, U sub K is for kinetic friction, and the static friction is always more than the kinetic friction. All right, so here's some different static and kinetic frictions. So like steel on steel is 0.74, okay, and U sub K is 0.57. Notice that there's no units on these things, and that's because it's a relationship, or it's a proportion, right? Mu is equal to force of friction over force normal, and we know that this guy has units of newtons, and this guy has units of Newton, and so if they both have units of Newton, they both cancel. So the mu has no units, okay? So on and so forth. So you can kind of look at these. So notice how like ice on ice, or Teflon on Teflon, right, has a really, really small coefficients of friction. The synovial joints, so these are the joints in like your knees and stuff like that, have very, very small coefficients of friction. Right? Oh. So, 24 kilogram crate initially at rest on a horizontal floor requires a 75 Newton horizontal force to set it in motion. Find the coefficient of static friction between the crate and the floor. Okay, so we need to find, so let's draw ourselves a little picture here. So we've got a crate sitting on a floor, all right, and it's 24 kilograms, all right, and it takes a 75 Newton horizontal force to set it in motion. So that's good that it's going just straight across, and that's 75 newtons. All right, so we need to find out what the coefficient of static friction is. Well, we know that the coefficient of friction is mu is equal to the force of the friction over the force of the normal. Okay, so mu is equal to the force of the friction over the force of the normal. Well, the force of the friction, they already told us, that's 75 newtons. All right, so that's 75. That's easy. All right, now we got to find out the force of the normal. Well, we know that in order to find the normal force, we have to know how much force it needs to beat gravity, right? So remember, the normal force is going to be pushing up like this, and gravitational force is going to be going like this. And because there's no other force helping it up, we know that the normal force has to be equal to the negative of the force of gravity. All right, and the force of gravity is simply the weight. Okay, so to find the normal force, all right, we're going to take the negative m times g. Okay, so the mass of this crate is 24, and the gravity, and we need to make it negative, and gravity is 9.81 meters per second squared. I'm sorry, this would give us, because we're taking this would be positive because the normal force, because the force of gravity is equal to negative mg, and then becomes positive. Anyway, so 24 times negative 9.81, 24 times negative 9.81, and we get 235.44 newtons. All right, so that's the normal force pushing up. Okay, all right. 1. All right, and then, so we'll plug that guy in there, 235.44. All right, so we'll take our 75 divided by that guy, and we get 0.32. And so our unit of, or coefficient of static friction is 0.32. Okay. All right, so we did all these steps. We drew a free body diagram, we found the weight, we found the normal force, we found the force of friction, and we got the right answer, 0.32. Look at us go. All right, now let's do it. Let's do a hard one, okay? So we've got a student attaches a rope to a 20-kilogram box of books, and he pulls the force of 90 newtons at a 30-degree angle at the horizontal, okay? So I know we've got a picture here, but I think we should draw another one just for grins and giggles. Make it a little bit easier. We have what's going on. So we've got a 20.0 kilogram pile of books, and then he's pulling up on it with a 90 Newton force at a 30-degree angle, okay, with the horizontal. All right. The coefficient of kinetic friction between the box and the sidewalks is 0.5. So it just tells us straight up that mu sub k is equal to 0.5. All right, find the magnitude of the acceleration on the box. All right, so let's think what we need in order to solve for this. All right, so we know that in order to find the acceleration, F equals ma, right? So that means our acceleration is going to be equal to force over mass. Force over mass. And that looks like an E. Let me change that so nobody gets confuzzled. All right, boop, boop. All right, acceleration equals force over mass. All right, so we've got the mass of our box. Our box is 20 kilograms. That's easy enough. But we need our force. Now remember, this is the net force. So we need to find the net force that's acting upon our box. So free body diagram, we've got a 90 Newton force going up this way, right? We've got some force of friction going this way. Force of friction. And we have some normal force going this way, and we've got some force of gravity coming this way. So we've got several forces that are acting on our box. All right, so what we need to solve for is we need to solve for the net force that's acting on our box. We know for sure that the total upwards force, because our box is not going up or down, right? We know it's only dragging horizontally. We know that whatever upwards force we have on the box is going to be equal to the downwards force, the gravity. Okay, so the force of gravity, okay, has to be equal to the force of the normal plus whatever this guy is. So if we think about this guy here, we've got a 90 Newton force that's pulling up like this. Well, we know that this is a resultant of two different components, an x component here and a y component here. So we'll say this is, we'll just call it tension y and then tension x. All right, so plus whatever the tension of the y is. So those two put together need to equal the force of gravity. So let's go ahead and solve for these guys because we're going to need these guys here. So, so we have this angle. This is 30 degrees. So we know how to find these values. So 30 times sine of 90. No, okay, I did it back. I was like, that can't be right. 90 times sine of 30. Whoops. 90 times sine of 30 is 45. Is that what I got before? Maybe I don't even need ty. Oh, I did 45. Okay. And then 90 times cosine of 30 is 77.9. All right, so 77.9. All right. All right, so that's this guy so far. So let's erase this and we'll add in these the components. All right, so we still have this information on the right, but now we're going to add in our new components. Okay, so we've got some pulling force this way. Okay, we called this Tx, and then now we also know we have this guy here, Ty. All right, so we need to find what our Fn is, okay? Because in order to find, remember, so in order to find out how effective, we know how hard we're pulling here. Now we're pulling at 77.9 newtons, but we don't know how hard friction's pulling back on us. So we need to figure out what the force of friction is. Well, we know that the force of friction is equal to mu times the normal force. And mu is equal to 0.5. They give it to us right here, but we need to find the normal force. But we know the normal force is equal to Fg plus Ty. So to solve for that, we can say that Fn is equal to Fg minus Ty. All right. So that means Fn is equal to Fg. Well, that's the force of gravity. So that's 20 times 9.81. Okay, minus Ty, which is 45, which is what we found before. All right, so that means our normal force is 20 times 9.81 minus 45. I got 151.2. So that's our normal force, 151.2 newtons. So that's our normal force that's pulling down. So that means our force of friction is equal to 0.5 times 151.2. All right, we're getting close. So times 0.5, and that's 75.6. All right. So let's redraw our box diagram real quick, our free body diagram. All right, just so we can all make sure we're on the same page. I'll do it over here. So we know that in our box that's being pulled, that there's some up and down, and they completely cancel each other, right? Because we're not going up and down, we're only going left and right. Now we know now that we've got a force going this way at 75.6 newtons, right? That's our force of friction. And then we also know that this way we have another force, the force of the being pulled, at 77.9 newtons. All right. So because of this, we know for sure that our box is going to be going to the right, okay? Because the force pulling to the right is greater than the force pulling to the left. So the net force is going to be pushing us to the right. All right. So really we just have to add up all these guys. So this is really a negative 75, and this is a positive 77. So our F net is going to be equal to the sum of all our forces. So that's a 77.9 minus or plus a negative 75.6, right? And this one's negative because it's pointed to the left. All right, so we take 77.9 minus 75.6, and we get 2.3 newtons. All right. All right, so that's our net force. All right, now that we have that, we simply have to take it back over. Remember this equation from way back when. So that means our acceleration is equal to the net force, which is 2.3, divided by the mass, which is 20. All right, so we'll take 2.3 divided by 20, and we get 0.12, which is exactly what we should have gotten. Well done, gang. Meters per second squared. I'm proud of you. Well done. All right. So that's about as hard as they get. All right, that would be a tough one. Okay. Make sure you're doing your practice problems so you know how to do that. Hopefully you learned your lesson about projectile motion. Do the practice problems. Okay. One last thing and then we're done with the unit. Okay. 4 fundamental forces. There's electromagnetic forces. These occur between protons and electrons. They produce friction. You can have gravitational force. We refer to this as the weak force because it takes a massive amount of mass in order for gravity to have much of an effect. Then there's the strong nuclear force. Very short range is the strong one, and the weak nuclear force is the weak force. So those are like the 4 fundamental forces that all other forces are acting on, have some sort of part in. You don't really have to know much about those, but you do. I just don't want you to have looked at them at least one time in your life, or at least before you get to college. All right, so that's it for Unit 2. Congratulations, you made it through all 6 parts of Unit 2. You've got a big lab coming up, and you've got the exam coming up as well. Anyway, so I'll talk to you guys later. Let me know if you have any questions, and good luck.